Welcome back to For Science Salah Lotfy channel. Today we embark on a journey into the heart of matter itself. We're diving deep into the fascinating world of plasma diagnostics. Plasma diagnostics is the key to unlocking the secrets of plasma, the often overlooked fourth state of matter. Plasma isn't just in stars or fusion experiments, it's all around us, from electronics to medical tools. But how do we study something as chaotic and energetic as a cloud of supercharged particles? That, my friends, is where the magic of plasma diagnostics comes in. Let's begin our exploration with electrostatic probes. Imagine a tiny wire, a sentinel of science inserted into the heart of a glowing plasma cloud. This is the Langmuir probe, the cornerstone of plasma diagnostics. By varying the voltage and measuring the current, we can determine the plasma's electron temperature, density, and electrical potential. For constantly shifting plasmas, we turn to the double probe, using two identical probes to unlock the plasma's secrets. And for capturing fleeting moments, we have the triple probe, providing real-time measurements of the plasma's vital signs. It's like taking a high-speed snapshot of the plasma's soul. These tools help us understand and harness the power of plasma. Now let's delve into the world of magnetic probes, also known as B-dot probes. These probes sense the subtle changes in the magnetic fields that envelop the plasma. Every ripple in the plasma's behavior leaves its mark on the magnetic field lines. These probes capture these signs by recording the induced voltage. Imagine a conductor loop placed near the heart of the plasma, capturing the magnetic field's dance. This is the essence of the B-dot probe, mapping the invisible forces shaping the plasma. With this knowledge, we can predict and control the plasma's behavior. Chapter 3. Microwave Methods. Peering through the plasma veil. For plasmas too hot for probes, we have microwave diagnostics. Microwaves can traverse extreme plasmas, revealing their secrets. A beam of microwaves aimed at the plasma is bent, scattered, and reflected. By analyzing these changes, we can unveil the plasma's secrets without direct contact. The cutoff frequency is a critical density point where the microwave signal is blocked. This intricate dance of waves and particles helps us understand the plasma's inner workings. Chapter 4. Spectroscopic Methods. Decoding the plasma rainbow. Plasma emits light, a radiant symphony of colors holding its deepest secrets. By analyzing the spectrum of light emitted by a plasma, we can unlock a treasure trove of information. Each element within the plasma emits light at specific wavelengths like a unique fingerprint. The width of these spectral lines can tell us about the plasma's density. A dense plasma produces broader spectral lines, while a less dense plasma exhibits sharper lines. The Doppler effect causes spectral lines to shift, revealing the temperature of the plasma's electrons. By measuring this shift, we can determine the speed and temperature of the electrons. The power of plasma diagnostics. Electrostatic probes measure plasma potential, density, and temperature. Magnetic probes track changes in magnetic fields. Microwave methods measure plasma density without direct contact. Spectroscopy unlocks the plasma's chemical and thermal secrets. Combining these tools provides a complete picture, turning invisible chaos into measurable science. Welcome back to For Science Salah Lotfy channel. Today, we're embarking on an illuminating journey into the fascinating world of laser systems. From the vibrant hues of dye lasers to the precision of Heine lasers, the industrial power of CO2 lasers, the unique mechanics of gas dynamic lasers, and the ultraviolet capabilities of excimer lasers, these technologies power countless aspects of modern science, industry, and even our everyday lives. So let's unlock the science behind these incredible beams of light. Our exploration begins with dye lasers, known for their remarkable versatility. Unlike traditional lasers that rely on solid-state or gas mediums, dye lasers harness the power of organic dye solutions. These solutions, often containing fluorescent dyes like rhodamine 6G, act as the heart of the laser, capable of emitting light across a broad range of wavelengths. In dye lasers, population inversion is achieved through a process called pumping, using sources like flash lamps or other lasers. This excites the dye molecules, propelling them to higher energy levels. As they return to their ground state, they release photons, creating the laser beam. One of the most remarkable features of dye lasers is their tunability. By carefully selecting the dye and adjusting the laser cavity, we can fine-tune the output wavelength across a wide spectrum, from the ultraviolet to the near-infrared. This incredible versatility makes dye lasers invaluable tools in various scientific fields. In spectroscopy, for instance, dye lasers allow us to probe the intricate energy levels within atoms and molecules. This ability to generate intense pulses of light makes dye lasers particularly well suited for applications like pulsed laser deposition. They can also operate in continuous wave mode, emitting a steady beam of light. In this mode, dye lasers can achieve power outputs of up to 2 watts with incredibly narrow line widths as fine as 1 kilohertz. Our journey through the world of lasers now takes us to the ubiquitous He-Ni laser, a true pioneer in the field. Unlike earlier lasers that produced light in short bursts or pulses, the He-Ni laser was designed to emit a continuous beam, a breakthrough that revolutionized laser technology. At the heart of this innovation lies a mixture of 2 noble gases, helium and neon. When an electrical discharge is passed through the gas mixture, the helium atoms get excited to higher energy levels. The excited helium atoms collide with the neon atoms, transferring their energy and exciting the neon atoms to a specific energy level. The excited neon atoms then transition back to their ground state, releasing photons of light in the process. These photons are emitted in a coherent beam, resulting in the characteristic red laser beam we associate with He-Ni lasers. The specific wavelength of this red light is 632.8 nanometers. The design of the He-Ni laser is remarkably elegant and robust. The glass tube containing the gas mixture is typically enclosed within a resonant cavity, formed by 2 mirrors placed at either end of the tube. This cavity amplifies the light produced by the neon atoms, ensuring a strong and stable laser output. The reliability and longevity of He-Ni lasers have made them a staple in various fields. Beyond their educational value, He-Ni lasers have found widespread use in barcode scanners, laser pointers, and even medical devices. Our exploration of laser technologies now takes us to the realm of CO2 lasers, renowned for their exceptional power and efficiency. These lasers, harnessing the energy transitions within carbon dioxide molecules, have become indispensable tools in industries ranging from manufacturing to medicine. At the heart of a CO2 laser lies a gas mixture primarily composed of carbon dioxide, nitrogen, and helium. To initiate the lasing process, an electrical discharge is passed through the gas mixture, energizing the molecules and setting the stage for light amplification. Nitrogen plays a crucial role in this process, transferring energy to the carbon dioxide molecules through collisions. The excited carbon dioxide molecules then transition between different vibrational and rotational energy levels, releasing photons of light in the process. These photons, emitted at a wavelength of around 10.6 micrometers, fall within the infrared region of the electromagnetic spectrum. One of the key advantages of CO2 lasers is their high efficiency. This efficiency, coupled with their ability to generate both continuous and pulsed outputs, makes CO2 lasers incredibly versatile. In industrial settings, CO2 lasers have become indispensable tools for cutting, welding, engraving, and marking a wide range of materials. In the medical field, CO2 lasers have revolutionized surgical procedures. Their ability to precisely target and ablate tissue with minimal bleeding and scarring has made them invaluable in various specialties. Our exploration of laser technologies now takes us off the beaten path to the fascinating realm of gas dynamic lasers. These lasers harness the power of thermodynamics to achieve population inversion, the fundamental principle behind laser operation. Imagine a chamber filled with a gas mixture, typically containing carbon dioxide, nitrogen, and water vapor. This mixture, initially at a high temperature and pressure, is suddenly allowed to expand rapidly through a supersonic nozzle. This rapid expansion creates a non-equilibrium condition where the vibrational energy levels of the gas molecules become overpopulated. This non-equilibrium condition is the essence of population inversion in a gas dynamic laser. The overpopulated vibrational energy levels create an ideal environment for stimulated emission, amplifying the light intensity. The expanding gas flows through an optical cavity, typically formed by 2 mirrors placed on either side of the flow. This cavity acts as a resonator, bouncing the emitted photons back and forth through the excited gas, further amplifying the light intensity. The result is a powerful laser beam, typically in the infrared region of the electromagnetic spectrum. Gas dynamic lasers are capable of generating extremely high power outputs, often in the kilowatt to megawatt range. This immense power output makes gas dynamic lasers suitable for specialized applications where conventional laser systems fall short. Our journey through the world of lasers culminates with excimer lasers, marvels of molecular engineering that have opened up new frontiers in ultraviolet light generation. These lasers, named after the excited dimers that form their active medium, have become indispensable tools in fields ranging from microelectronics to medicine. Unlike other lasers that rely on atoms or stable molecules, excimer lasers harness the unique properties of excimers, short-lived molecules that exist only in an excited state. These excimers are typically formed by combining a noble gas, such as argon or krypton, with a halogen, such as fluorine or chlorine. When subjected to an electrical discharge in the presence of a halogen, these noble gases can be coaxed into forming temporary bonds, creating excimer molecules. These excimer molecules, existing only in an excited state, are inherently unstable and short-lived. As they transition back to their ground state, they release their energy as photons of light. The wavelength of light emitted by an excimer laser is determined by the specific excimer molecule involved. This ability to generate ultraviolet light, a region of the electromagnetic spectrum with higher energy photons than visible light, is what makes excimer lasers so unique and valuable. In microelectronics, excimer lasers have become indispensable tools for photolithography, a process used to create intricate patterns on semiconductor wafers. In medicine, excimer lasers have revolutionized eye surgery, particularly in procedures like LASIK. So today we've explored an exciting lineup: dye lasers, He-ni lasers, CO2 lasers, gas dynamic systems, and excimer lasers, each unlocking new frontiers in research, manufacturing, and healthcare. From the vibrant colors created by dye lasers to the industrial power of CO2 lasers and the ultraviolet precision of excimer lasers, these technologies showcase the incredible versatility and power of light amplification by stimulated emission of radiation. We at For Science Salah Lotfy channel would like to extend our gratitude to Professor Dr. Tarek Nagla from the Nuclear Power Plants Authority, Egypt, for his invaluable scientific support. His expertise and insights continue to inspire us to explore and explain the wonders of science. And thank you, our brilliant audience, for your curiosity and engagement. Don't forget to like, share, and comment below. Lasers are amazing tools. They produce highly focused beams of light. Excimer lasers are a special type of laser. They generate light in the ultraviolet range. This makes them incredibly useful for a wide variety of applications. Unlike your typical laser pointer, excimer lasers pack a punch. They are high-energy devices. This makes them suitable for tasks that require precision and power. Think of them as the industrial strength versions of your average laser. Excimer lasers get their name from the unique molecules they use to generate light. These molecules are called excited dimers. We'll delve into the specifics of these molecules in the next section. The heart of an excimer laser lies in its unique molecular composition. These lasers employ a special mixture of gases. This mixture includes a noble gas such as argon, krypton, or xenon. A halogen gas like fluorine or chlorine is also added. Normally these gases wouldn't interact much, but within the laser they are energized by a powerful electrical discharge. This energy jolt forces them to form temporary molecules called excimers. These excimer molecules are inherently unstable. They exist for only a brief moment. This instability is what makes them so valuable. When they break down, they release the energy they absorbed in the form of ultraviolet light. Excimer lasers are known for their ultraviolet emissions. UV light is invisible to our eyes, but it carries more energy than visible light. This makes it very useful for various applications. The exact wavelength of UV light emitted depends on the specific gases used in the laser. For example, an argon fluoride excimer laser emits UV light with a wavelength of 193 nanometers. A krypton fluoride laser, on the other hand, emits at 248 nanometers. These specific wavelengths are chosen for their effectiveness in various applications. Section 4. Inside the excimer laser, a symphony of energy. The design of an excimer laser is fascinating. It all starts with a gas-filled chamber. This chamber contains the mixture of noble gases and halogens. High-voltage electrodes are strategically placed within the chamber. When a high-voltage pulse is applied to the electrodes, it creates an electrical discharge within the gas mixture. This discharge excites the gas molecules, leading to the formation of those short-lived excimer molecules. As the excimer molecules decay, they release their energy as pulses of ultraviolet light. To ensure efficient and uniform excitation of the gas mixture, excimer lasers often employ a technique called pre-ionization. A separate, brief electrical pulse is used to pre-ionize the gas just before the main discharge. This pre-ionization step helps create a more conductive path for the main discharge, resulting in a more powerful and uniform laser beam. Section 5. Shaping our world. Applications of excimer lasers. Excimer lasers are found in a wide range of applications. Their unique properties make them indispensable in various fields. One of the most well-known applications is in microelectronics. Excimer lasers are essential for photolithography, a process used in the manufacturing of computer chips. The ultraviolet light from these lasers is used to etch intricate circuit patterns onto silicon wafers, creating the complex microchips that power our computers and smartphones. In medicine, excimer lasers have revolutionized eye surgery. They are used in procedures like LASIK, where the laser's precision allows surgeons to reshape the cornea and correct vision problems. Beyond microelectronics and medicine, excimer lasers are also employed in material processing. They can be used to cut, drill, and mark a variety of materials with high precision, making them valuable tools in manufacturing industries. The significance of excimer lasers in modern science and technology cannot be overstated. From the smartphones we use daily to the advancements in medical technology, excimer lasers have played a pivotal role in shaping our world. As we continue to develop new technologies and push the boundaries of scientific exploration, excimer lasers will undoubtedly remain essential tools in our quest for knowledge and innovation. The universe is filled with light. Stars, galaxies, and even our own sun emit light that travels vast distances across space and time. But there's a special kind of light that we've harnessed here on Earth: laser light. Unlike the light from a light bulb, which spreads out in all directions, laser light is focused and intense. This unique property makes lasers incredibly versatile tools, used in everything from telecommunications to medicine. At the heart of every laser lies a crucial component: the laser resonator. Imagine a chamber where light bounces back and forth, gaining intensity with each pass. That's essentially what a laser resonator does. It's a carefully designed cavity, usually formed by mirrors, that traps and amplifies light, transforming it from a faint glow into a powerful beam. The journey of understanding and harnessing laser light began in the early 20th century. Scientists like Albert Einstein laid the theoretical groundwork for lasers with their groundbreaking work on the nature of light and atoms. But it wasn't until the 1960s that the first working lasers were built, ushering in a new era of technological advancements. Laser resonators are the unsung heroes of the laser world. They are the engines that power these remarkable devices, enabling us to manipulate light in ways never before imagined. Understanding how they work is key to unlocking the full potential of laser technology. Imagine a hall of mirrors at a carnival. Your reflection bounces from one surface to another, creating an endless illusion of depth. A laser resonator works in a similar way, but with a crucial difference. It amplifies the light with each reflection. A laser resonator consists of at least two mirrors placed facing each other. These mirrors are highly reflective, meaning they bounce back most of the light that hits them. Inside the resonator, a light-emitting material called the gain medium is stimulated to release photons, the tiny packets of energy that make up light. These photons don't just radiate randomly in all directions. Instead, they are guided by the resonator's mirrors, bouncing back and forth through the gain medium. With each pass, more photons are emitted, amplifying the light intensity. This process continues, creating a cascade of photons all traveling in the same direction, resulting in a highly focused, coherent beam of laser light. The type and arrangement of mirrors used in a resonator determine the properties of the laser beam it produces. Different resonator designs have been developed over the years, each with its own advantages and applications. Understanding these designs and how they influence the characteristics of laser light is crucial for developing new and innovative laser technologies. The simplest and most fundamental type of laser resonator is the Fabry-Perot resonator. Named after its inventors Charles Fabry and Alfred Perot, this resonator consists of two parallel mirrors placed a certain distance apart. Imagine these mirrors as two walls of a long, narrow room. Light introduced into this room bounces back and forth between the mirrors. Only light waves of specific wavelengths, which correspond to the distance between the mirrors, can exist within this resonator. These wavelengths are called resonant frequencies. Think of a guitar string. When you pluck it, it vibrates at specific frequencies, producing the notes you hear. Similarly, a Fabry-Perot resonator selects and amplifies only specific light frequencies, creating a highly monochromatic laser beam, meaning it consists of a very narrow range of colors. The distance between the mirrors, known as the cavity length, plays a crucial role in determining these resonant frequencies. By adjusting the cavity length, we can fine-tune the color of the laser light emitted. Fabry-Perot resonators are widely used in various applications, including telecommunications, spectroscopy, and laser scanning. Their simplicity and versatility make them an essential building block in the world of lasers. While Fabry-Perot resonators excel in simplicity, spherical resonators introduce a new level of control over laser beams. Instead of flat mirrors, they employ curved mirrors to confine and shape the light. Imagine a whispering gallery, where sound waves travel along the curved walls, becoming focused at certain points. Spherical resonators work similarly, using curved mirrors to guide the light in a circular path. This curvature introduces a focusing effect, concentrating the light energy into a smaller area. The mathematical description of spherical resonators involves concepts like the radius of curvature of the mirrors and the distance between them. These parameters determine the stability of the resonator and the shape of the resulting laser beam. One common type of spherical resonator is the confocal resonator. In this configuration, the focal points of the two mirrors coincide, creating a stable and well-defined beam waist, the point where the laser beam is narrowest. Spherical resonators offer several advantages over their planar counterparts. They provide better confinement of the laser mode, leading to higher output power and improved beam quality. Moreover, their focusing properties make them suitable for applications requiring tight focusing, such as laser cutting and engraving. Section 5. Confining light. The importance of stability. Imagine trying to bounce a ping-pong ball between two paddles. If the paddles are perfectly aligned, the ball bounces back and forth predictably. But if the paddles are even slightly misaligned, the ball quickly veers off course. Similarly, laser resonators need to be stable to ensure that the light bounces back and forth between the mirrors without escaping. The stability of a resonator depends on the curvature of the mirrors and the distance between them. If these parameters are not chosen carefully, the laser beam can become unstable, leading to a loss of power and unpredictable behavior. One way to visualize resonator stability is through stability diagrams. These diagrams, often used by laser engineers, plot the stability regions for different resonator configurations. By choosing parameters within these stable regions, we can ensure that the laser operates reliably. Diffraction, the bending of light waves around obstacles, also plays a role in resonator losses. Even with perfectly aligned mirrors, some light will inevitably diffract out of the resonator, reducing its efficiency. Minimizing diffraction losses is crucial for achieving high-power lasers. This can be achieved by using larger mirrors, optimizing the resonator geometry, and minimizing the number of optical elements within the cavity. Section 6. Gaussian Beams. The shape of laser light. Laser light, unlike the light from a light bulb, doesn't spread out uniformly. Instead, it takes on a special shape known as a Gaussian beam, named after the mathematician Carl Friedrich Gauss. Imagine a bell curve, the familiar shape used to represent statistical distributions. A Gaussian beam has a similar profile with the highest intensity at the center, gradually decreasing towards the edges. This characteristic shape is a result of the way light interacts with the resonator mirrors. Gaussian beams are characterized by their beam waist, the point where the beam is narrowest, and their divergence, the angle at which the beam spreads out as it propagates. The beam waist and divergence are determined by the resonator geometry and the wavelength of the laser light. The Gaussian beam profile is crucial for many laser applications. Its high intensity at the center makes it ideal for focusing to a small spot, essential for laser cutting, printing, and surgery. Moreover, the low divergence of Gaussian beams allows them to travel long distances with minimal spreading, making them suitable for telecommunications and LiDAR systems. Understanding the properties of Gaussian beams is essential for designing and optimizing laser systems for various applications. Section 7. From Atoms to Light. Understanding population inversion. At the heart of every laser lies a fascinating quantum mechanical phenomenon, population inversion. To understand this concept, we need to delve into the world of atoms and their energy levels. Imagine an atom as a tiny solar system with electrons orbiting the nucleus like planets around a star. These electrons can exist at different energy levels, much like planets can occupy different orbits. When an electron jumps from a higher energy level to a lower one, it releases energy in the form of a photon, a particle of light. In a normal material, most atoms are in their ground state, meaning their electrons occupy the lowest energy levels. However, by pumping energy into the gain medium, we can excite the atoms, causing their electrons to jump to higher energy levels. Population inversion occurs when we create a situation where more atoms are in an excited state than in the ground state. This is a necessary condition for laser operation because it creates the potential for stimulated emission. Stimulated emission is the process by which an excited atom, when it interacts with a photon of the right energy, is stimulated to release a second photon identical to the first. This process is responsible for the amplification of light within the laser resonator. Section 8. Resonators in action applications in our daily lives. Laser resonators, though hidden within the intricate workings of lasers, play a crucial role in countless technologies we rely on every day. In telecommunications, lasers transmit vast amounts of data through fiber optic cables, forming the backbone of the internet. In medicine, lasers are used for precision surgery, correcting vision, and removing tattoos. In manufacturing, lasers cut, weld, and engrave materials with incredible accuracy. Barcode scanners, laser pointers, and even the CD and DVD players we use for entertainment all rely on the precise control of light made possible by laser resonators. From scientific research to entertainment, lasers have revolutionized numerous fields, and their impact continues to grow. As we develop new materials and resonator designs, we unlock even more possibilities for laser technology. The future holds exciting prospects for lasers in areas such as quantum computing, advanced imaging, and high-energy physics research. Section 9. The Future of Light, Advancements and Possibilities. The journey of laser technology is far from over. Researchers around the world are constantly pushing the boundaries of what's possible with lasers, exploring new materials, resonator designs, and applications. One exciting area of research is the development of metamaterials, artificial structures with optical properties not found in nature. Metamaterials could lead to the creation of compact, highly efficient lasers with unprecedented control over light. Another promising avenue is the development of quantum cascade lasers, which operate on different principles than traditional lasers. Quantum cascade lasers can emit light in the mid-infrared and terahertz regions of the electromagnetic spectrum, opening up new possibilities for sensing, imaging, and spectroscopy. As our understanding of light and matter deepens, so too will our ability to manipulate and control it. Laser resonators, the unsung heroes of the laser revolution, will continue to play a vital role in this ongoing journey of discovery and innovation. The future of light is bright, and with it comes the promise of transformative technologies that will shape the world around us.
Have you ever wondered how lasers, those beams of pure, intense light, actually work? The answer lies in a fascinating component called a laser resonator. This ingenious device is the heart of every laser, responsible for generating the powerful, focused light we use in countless applications. Like an echo chamber for light, a laser resonator traps and amplifies light, transforming it into the laser beam we know and rely on. Without resonators, lasers wouldn't exist. These devices are essential for everything from scanning groceries at the supermarket to performing delicate eye surgery. Understanding how they work unlocks the secrets behind one of the most important inventions of the 20th century. Imagine two mirrors facing each other, much like a light bouncing back and forth between them. That's the basic idea behind a laser resonator. This simple setup, while seemingly straightforward, is the foundation for generating laser light. But it's not just about bouncing light. Between these mirrors lies a special material called the gain medium. This medium could be a gas, a crystal, or even a semiconductor. and it's responsible for amplifying the light as it passes through. With each reflection, the light gains more energy, becoming more and more intense. Think of a laser resonator like a pinball machine for photons, those tiny packets of light energy. Each time a photon bounces off a mirror, it travels through the gain medium, picking up energy along the way. This process, called stimulated emission, is the key to laser light. As more and more photons bounce back and forth, they begin to synchronize, aligning their waves and creating a cascade of light with the same wavelength and direction. This coherent light is what makes laser beams so special, allowing them to travel long distances without spreading out and delivering focused energy. In the early days of lasers, scientists were puzzled by how the light inside the resonator stabilized into a coherent beam. Two physicists, Alan Fox and Tingyi Li, made a groundbreaking discovery in 1961. They used a computer to simulate the behavior of light inside a resonator, painstakingly calculating the path of light rays after each reflection. What they found was remarkable. After many reflections, the initially random pattern of light settled into a stable and predictable shape. This discovery, known as the Fox and Lee condition, revolutionized our understanding of laser resonators and paved the way for designing more efficient and powerful lasers. Not all laser resonators are created equal. Each design has its own unique strengths and limitations, which play a crucial role in how the laser performs in real-world scenarios. They can be broadly classified into two main types, stable and unstable resonators, each with distinct characteristics that affect the behavior of the laser beam. Stable resonators, as their name suggests, keep the light trapped within the cavity, allowing it to bounce back and forth many times. This repeated reflection helps to refine the beam and maintain its quality. This leads to a highly directional, focused laser beam, which is ideal for applications that require precision and accuracy. Unstable resonators, on the other hand, allow some light to leak out with each pass. This design might seem less efficient at first glance, but it serves a specific purpose. While this might seem counterintuitive, it's actually beneficial for certain applications where high output power or unique beam shapes are needed. Unstable resonators can handle higher power levels and produce beams with different shapes, making them especially suitable for demanding industrial tasks like cutting and welding. The choice between a stable and unstable resonator depends on the specific application of the laser as well as the desired beam quality and power. For example, barcode scanners use stable resonators for their precision and reliability in reading fine details, while high-power lasers used in manufacturing often employ unstable resonators to achieve the necessary energy and beam profile for processing tough materials. Understanding how light behaves inside a laser resonator is crucial for designing efficient lasers. To do this, scientists use a technique called ray tracing. Imagine drawing lines to represent the path of light rays as they bounce between the mirrors. By carefully calculating the angles and distances involved, we can predict how the light will travel and interact with the gain medium. This method, based on the paraxial wave equation, helps us visualize and optimize the resonator's geometry. By adjusting the curvature of the mirrors, the distance between them, and the position of the gain medium, we can manipulate the light's path and achieve the desired output beam characteristics. As light bounces back and forth within a stable resonator, it gradually takes on a special shape, a Gaussian beam. This transformation isn't random, it's a direct result of the physics inside the laser cavity, where only certain patterns of light can survive repeated reflections. This bell-shaped profile is the most efficient way to confine light within the resonator, minimizing losses and maximizing output power. The Gaussian beam's smooth, symmetrical shape allows it to travel long distances without spreading out too much. Imagine a beam of light that's brightest at its center and gradually fades towards the edges, creating a soft, natural fall-off that's easy to recognize in many laser applications. That's the essence of a Gaussian beam, a perfect balance between focus and spread, making it ideal for precision tasks. This unique shape arises from the wave nature of light and the way it interacts with the curved mirrors of the resonator, which guide and shape the beam with incredible accuracy. Matching the shape of the resonator mirrors to the Gaussian beam profile is crucial for optimal laser performance, ensuring the beam remains stable and intense. This careful design ensures that the light is efficiently reflected and amplified, leading to a powerful and well-defined laser beam that's ready for use in everything from scientific research to industrial cutting. Laser resonators are the unsung heroes of countless technologies we use every day. From scanning groceries at the checkout to playing music on CD players, laser resonators are everywhere. In medicine, they are used for precise surgery, correcting vision, and removing tattoos. In industry, they cut and weld materials with incredible accuracy, manufacture microelectronics, and even enable high-speed internet through fiber optic communication. The applications of laser resonators are as diverse as the imagination. As our understanding of light and its interaction with matter deepens, we continue to find new and innovative ways to harness the power of laser resonators. Laser resonators, those ingenious devices that trap and amplify light, have become the backbone of modern photonics and optical science. They have revolutionized science and technology, enabling breakthroughs that were once thought impossible. From the mundane to the extraordinary, their applications improve our lives in countless ways, from precision manufacturing to life-saving medical procedures and even the devices we use every day. As we continue to explore the frontiers of light and its interactions with matter, new discoveries are constantly being made, pushing the boundaries of what lasers can achieve. The future of laser technology promises even more exciting possibilities, from quantum computing to advanced communications and beyond. By understanding the principles behind laser resonators, we gain the ability to harness and direct light with incredible precision. This allows us to unlock the secrets of controlling and manipulating light itself, opening doors to innovations we can only begin to imagine. This knowledge empowers us to develop new technologies and address some of the world's most pressing challenges, from clean energy to global connectivity. The journey into the hidden world of laser resonators is a testament to human ingenuity and our relentless pursuit of understanding the universe around us, inspiring future generations to keep pushing the limits of what light can do.
Lasers are amazing. They are one of the most fascinating inventions of modern science. They make focused beams of light that can travel long distances without spreading out. These beams have special properties. They are different from regular light because they are coherent and monochromatic. We use lasers in many ways. They are in our homes, hospitals, and even in space. Their versatility is unmatched. Lasers can cut through metal with precision. They can also transmit information over vast distances. Doctors use lasers for surgery, making procedures less invasive. Scientists use lasers to study the universe and uncover its secrets. Understanding laser light helps us use it better and innovate new applications for the future. Laser light is special. It's called a Gaussian beam. This name comes from its shape. Imagine a beam of light like a bell curve. That's a Gaussian shape. Gaussian beams have a waist. This is where the beam is the narrowest. The beam spreads out as it moves away from the waist. We use math to describe this spread. We can change the shape of a Gaussian beam. We use lenses to do this. Lenses are curved pieces of glass. They bend light in specific ways. A convex lens makes the beam converge. This means the beam comes to a point. A concave lens spreads the beam out. Lenses help us control Gaussian beams. We can focus a Gaussian beam to a very small spot. This is called the focal spot. The size of the spot is important. A smaller spot means more energy is concentrated. This is useful for cutting and engraving. We use focused lasers in manufacturing and medicine. Section 5. Telescopes, expanding our view of light. Telescopes use lenses to magnify distant objects, allowing us to see things far away. They can also expand laser beams, making them useful in various scientific applications. There are different types of telescopes, each designed for specific purposes. Two common types are Galilean and astronomical telescopes. Galilean telescopes use a convex and a concave lens to focus light. Astronomical telescopes use two convex lenses to gather more light. Both types can expand beams, but they do it in different ways, enhancing our understanding of light. Section 6. Guiding light trapping beams. We can trap light in a waveguide. This is like a pipe for light. Optical fibers are a type of waveguide. Waveguides keep light from spreading out. They use special materials to confine the light. This is important for communication and medical imaging. Section 7. Laser Resonators. Building a light amplifier. Lasers use something called a resonator. This is a cavity with mirrors. Light bounces back and forth between the mirrors. The mirrors have to be precisely aligned. The distance between them is also important. This creates feedback and amplifies the light. Section 8. Conclusion. Lasers and Gaussian beams everywhere. Lasers and Gaussian beams are everywhere, from the labs to the streets. We use them in many applications, from entertainment to communication. They are essential for modern technology, enabling advancements we rely on daily. Understanding these concepts helps us appreciate their importance and potential. From barcode scanners to fiber optic internet, lasers are integral. Gaussian beams are shaping our world in countless ways. As we continue to study light and its properties, we will discover even more amazing applications that will transform our future.